Welcome and thank you for joining us today for our Monash Prato Dialogue Distinguished Lecture Series in Artificial Intelligence. I'm Jeff Webb, Research Director of the Monash Data Futures Institute here at Monash University, and I'm your host and moderator for today. Before we begin, I wish to acknowledge the people of the traditional lands on which we are joining together today. I'm on the lands of the people of the Kulin Nations, and I pay my respects to their elders, past and present. Please join us in the conversation on social media by following us on Twitter at Monash DFI and by using the hashtag Monash Prato Dialogue. The Monash Data Futures Institute is the largest interdisciplinary community of AI and data science thought leaders in Asia Pacific, and we're committed to excellence and shaping the future of the field. Within the Institute, our focus areas include the use of data-driven AI across research in governance and policy, sustainable development, and health sciences. This new Monash Prato Dialogue Distinguished Lecture Series aims to explore the evolving impact of data science and AI in society by fostering a global dialogue. This series takes its name from Monash University's centre in Prato, Italy, that represents an international base for research, education, intellectual and cultural exchange, and enables us to bring people together to meet, learn, and collaborate with peers and colleagues from around the world. You've joined us today for the fifth lecture in this series, where we are delighted to host Professor Milind Tambe. Professor Tambe is Gordon McKay Lecturer of Computer Science and Director of the Centre for Research on Computation and Society at Harvard University. He's also Director of AI for Social Good at Google Research, India. Professor Tambe is a fellow of the AAAI, Association for Advancement of Artificial Intelligence, the ACM, Association for Computing Machinery, as well as recipient of the IJCAI John McCarthy Award, AAAI Robert S. Engelmore Memorial Lecturer Award, ACM SIG-AI Autonomous Agents Research Award, the Columbus Fellowship Foundation Homeland Security Award, the Informs Wagner Prize for Excellence in Operations Research Practice, among others. In today's lecture, Professor Tambe will focus on the problems of public health and conservation and address how to effectively deploy our limited intervention resources in these problem domains. That's all from me. Over to you now, Milind. Thanks for joining us today.
Well, thank you for this invitation. Thank you all for joining, and thank you for this kind introduction. So let me share my screen now. All right, so I'm just going to jump right into the topic at hand. For the past 15 years, my team and I have focused on advancing AI and multi-agent systems research for social impact, focusing on topics of public health, conservation, and public safety and security. Key challenge, how to optimize our limited intervention resources. I'm going to jump right into the lessons that we've learned. Lesson number one, achieving social impact and AI innovation go hand in hand. With respect to public health, we have large populations to serve but limited public health resources. Concrete example is work we have done with youth experiencing homelessness in Los Angeles. Harnessing the social networks of these youth, we are able to show that our influence maximization algorithms are far more effective in reducing HIV risk behaviors compared to traditional approaches. This work required innovation in the area of social network algorithms and bandit algorithms. With respect to conservation, we have large conservation areas to protect, but limited number of ranger resources. Concrete example is work we have done in Uganda and Cambodia, where harnessing past poaching data, we are able to remove thousands, if not tens of thousands of snares. This work required innovation in the area of what we call green security games, which combines machine learning and game theory. Previously, in the area of public safety and security, we've contributed a new model called Stackelberg Security Games and contributed new algorithms that have been in use by security agencies in the United States, such as the US Coast Guard, the Federal Air Marshals, and others. Today's talk will focus on public health and conservation. Now, it may appear that these are very different application areas. However, they are tied together by underlying models that are common, that are borrowed from the area of AI called multi-agent systems. Lesson number 2 is all of this work is only possible because of partnerships with communities and nonprofits. I've put some logos here of the nonprofits that we've worked with. Our ultimate goal is to empower these nonprofits to use AI tools and avoid being gatekeepers to AI technology for social impact. Lesson 3 is that when doing AI for social impact, we have to look at the entire data to deployment pipeline, and it's beyond just improving algorithms. We begin our work by immersing ourselves in the domain, trying to understand the type of data that are available, the kinds of problems that are faced by a nonprofit. Following that, a predictive model makes predictions on which of the cases faced by a nonprofit are high risk versus low risk. Following that, a prescriptive algorithm tells us which cases to actually intervene on. Given limited resources, we can't intervene on all of the cases. So that's where our multi-agent reasoning becomes important. And finally, field testing and deployment is important not only because we want to test our models and algorithms, but because social impact itself is a key objective of our research. So in this talk, I'm going to present to you 4 projects, 3 in public health, 1 in conservation. In each project, you will see a combination of a technique, such as restless bandage, and an application, such as maternal and child care. I'll cover papers from conferences such as AMAS, AAAI, ICHCA, and so forth for the last 4 years from my research group from 2017 to now. I'll focus on real-world results mostly, but there are simulations in our papers that I'll cite. And I'll highlight the role of the key PhD students and postdocs by putting up their pictures in the top right-hand corner. So I see somebody has put a comment in the chat. I'm going to leave it there. If it's important, I hope somebody will point out that to me. But I hope you're able to hear me well. So let's begin by talking about social networks and HIV prevention. So this work was motivated by what I saw in Los Angeles. I was in Los Angeles for many years, and there's 6,000 youth who sleep on the streets of Los Angeles every night. The rates of HIV in this population are 10 times the rates of normal house population. And our goal is to prevent HIV in youth experiencing homelessness. Now, homeless shelters will try to do this by recruiting a limited number of peer leaders. We can't go and talk to every one of those 6,000 youth. So we recruit a limited number of peer leaders, educate them about HIV prevention, expect them to talk to their friends and their friends to talk to their friends. And in this way, information to spread in the social network. This is real face-to-face interaction. This is not happening over Facebook, etc. So imagine in this case, we are given this social network. Each number here is a youth experiencing homelessness. A red line is an edge between 2 nodes, is a friendship of those 2 youth. And now we are going to select a few peer leaders so as to maximize the expected number of influence nodes, those who get educated about, informed about HIV prevention. So here's a picture of our social work colleague educating peer leaders about HIV prevention. Information spreads in the social network via this, what we model as an independent cascade model. So when we inform youth C about HIV prevention, adjacent youth, their friend D, will be informed with a probability of 0.4. And when D is informed, they may inform their friends E with a probability of 0.4. So information will cascade in this network. Now, there is a significant amount of work of it already in the area of influence maximization. Why can't we use that directly? It turns out there are 3 key challenges that arise, and they all arise, and this is lesson 4, because of lack of data and uncertainty, which is a key feature of AI for social impact. I said 0.4 as the propagation probability, but we do not know that propagation probability exactly. I said we can recruit peer leaders and educate them about HIV prevention, but several peer leaders may be no-shows. So we have to have dynamic policies to recover from the fact that some of our peer leaders are no-shows. And the social network itself is unknown. All we can do is do a limited amount of querying to find a small sample of the network. So I'm going to sketch some ways that we solve these problems. The first is the fact that we do not have the exact probability known to us. That's when C is informed, there'll be a probability 0.4 that youth D will be informed. So to model this uncertainty, we can model it as sampling from some distribution, but the mean of the distribution itself may not be known. So we may say that this lies within some interval. So given this uncertainty over propagation probability, now we are faced with the problem of robust influence maximization. And we solve this as a zero-sum game against nature. In other words, our algorithm is trying to choose peer leaders to maximize our payoff, maximize the number of people informed, when nature is trying to choose parameter settings to cause our algorithms to perform as worse as possible. So we are trying to maximize and nature is trying to minimize, where the payoff is a ratio of the outcome of our particular choice of peer leaders to the optimal that would be possible had we known nature's choice of parameter settings ahead of time. There are details here about choosing a mixed strategy and from there obtaining a pure strategy and so forth. I'm going to leave that aside. Those details are in our Armand's paper, and talk to you a little bit about how we solve this game. The difficulty here is that if you imagine a social network of 400 nodes, and from there we are trying to select 40 youth. That's 400 choose 40. That's a large number of policies that an influencer can choose. Nature is trying to choose parameter settings from a continuous interval. So nature also has a very large number of strategies to choose from. In other words, the game is so massive, representing it in memory is difficult, let alone trying to solve it. So to solve these kinds of games, we use a double oracle approach. We initialize this game with a small number of strategies randomly chosen on both sides. And then there's this iterative process where an influencer's oracle will add its next best choice of policy. Nature's oracle will add its next best choice of parameter settings. The game will grow, and we iterate in this fashion until convergence, and we can show that we can converge with approximation guarantee. So this is how we solve the problem of robust influence maximization, by making this a game against nature. The second problem is we don't have the full social network in hand. You could imagine sending our social network, social work colleagues into a homeless shelter and then checking with every single youth who their friends are and so forth, and then collecting the entire social network of the youth in that particular homeless shelter. But this is expensive. If we want to use this process in different homeless shelters, this is not going to work. Instead, if we can query a small fraction of the nodes, query a small number of, say, 50 peer leaders having known a sample of this network to spread influence, such that the performance is similar to opt, the best influence spread possible had we known the full network. That's what we want. So we're going to query a few of these youth to ask who their friends are. And that's all the information we get about the social network. And we do so by sampling nodes randomly and estimating sizes of the communities they belong to, and then choosing seeds from the largest K communities. In our AAAI paper, we are able to provide some theoretical guarantees about this algorithm. But let me now turn to the actual experiment that we ran. We built a system called Change, which is a combination of the network sampling I just mentioned, the robust policy generation I mentioned. There's also multi-step policy that's needed. And that's how we select peer leaders, the ones we are going to use to spread information about HIV prevention. So we conducted a study. This is with 750 youth with Professor Eric Rice in the School of Social Work at USC. There's 3 arms in the study. First, 250 youth are in the change partition. Here, we are going to select peer leaders based on change, as I mentioned here. Second is degree centrality. This is the traditional approach. Bring in the most popular youth, the youth with the largest degree in terms of degree centrality. And the third is the control group where there is no intervention at all. So we select peer leaders in each group according to that particular algorithm, change or degree centrality or no intervention, that is the control group. And then we look at 1 month after the intervention and 3 months after the intervention to see, was there an actual reduction in HIV risk behaviors? So this is work that is looking at actual reduction in HIV risk behaviors. As far as we know, the first large-scale application of these influence maximization algorithms for public health in the real world. It was done in collaboration with 3 homeless shelters: My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. And in each case, as I said, there were 750 youth. We are looking at 250 in each partition, and we look at how was the change in behavior at the end of a month. And here's what we find. In terms of reduction in condomless anal sex, in terms of change, there was more than 30% reduction at the end of 1 month. With respect to degree centrality and control group, however, there was no reduction at all. At the end of 3 months, we find that degree centrality begins to catch up with change. However, change is still better. And the fact that change was able to achieve this improvement, this reduction just in 1 month, is significant because this is a community where people come and go, and also because this is an HIV risk behavior. So making this reduction faster is important. We see similar behavior in terms of condomless vaginal sex. Again, change performs better. There's statistical significance results in our papers, if you wanted to look at those. And here's what
a way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
So that's our partner, Alison Hurst from Safe Place for Youth. In terms of next steps beyond, one area is fairness. If we look at how influence spreads, we see that if you look at different groups, then there may be disparities in where influence gets spread in terms of different racial groups or other groups and so forth. So we're trying to address this issue of fairness via maximum fairness in our NIRS 29 paper, which maximizes the minimum utility of any community. Diversity constraints in our HCI 29 paper, HCI 19 paper, which looks at an approach from cooperative game theory. But each of these approaches offers a point solution, a point trade-off between performance and fairness. Instead, in our AAAI paper recently, we've looked at providing a policymaker with a control, a particular parameter that they can set in order to make that trade-off between fairness and performance. A second area of future work is looking at reinforcement learning as a way of trying to solve the problems that I mentioned. So far, we've looked at it in terms of smaller portions of the problem. So for example, instead of the network sampling that I showed, could we use reinforcement learning for network sampling and then do influence maximization? It turns out that reinforcement learning does better than our hand-drawn algorithm. We also looked at speeding up influence maximization. Turns out that with reinforcement learning, if you train on similar graphs from other sources and then test it on the ground, the performance is similar to change, but of course it runs very fast. So these are things that we are trying that shows the power of reinforcement learning brought to bear on smaller pieces of the problem. Integrating it all together and testing it in the field remains a very exciting issue for future work. Let's now switch gears and talk about some work we did at Google Research India. And this is in the field of maternal and child care. In India, the situation on maternal child care is difficult. A woman dies in childbirth every 15 minutes. 4 out of 10 children are too thin or short. And so we're very fortunate there to work with a nonprofit called Armand that works with 25 million women. One of their programs is called M-Mitra. It's a weekly 2-minute automated message to new or expecting mother. The message may be of the form, you are 6 weeks into pregnancy, you should use this health supplement. Or your child is 6 weeks old, enroll them in this particular government program. So in randomized control trials, Armand has shown that M-Mitra brings significant benefits to women and their babies. 2.2 million women have enrolled in M-Mitra. Where do we come in? Unfortunately, a significant fraction, 30 to 40% of the women may become low listeners. So they may enroll, but become low listeners over time. So Armand has limited intervention resources. They can give service calls to a small fraction of these beneficiaries to try to retain them in the program. The question is, which beneficiaries should receive a service call? So supposing we have 200,000 beneficiaries who have enrolled, and we are trying to choose 4,000 per week to give service calls to. The basic goal here is to maximize the number of health messages that are being listened to by these mothers. So imagine now I'm a particular health center worker. I'm imagining here just 5 beneficiaries in our care. 4 of them are in red. They have not listened to any health messages. 1 of them is in green, has listened to this health message in this week. And this health worker now has to decide which 2 women, in this example, she can only call 2 women per week, which 2 beneficiaries should she call? Supposing she calls the first 2, this is a good choice because these 2 turned green. They started listening to messages from next week. There's an additional mother who also started listening. She also turned green, but there's 2 who are still red. So now the health worker may say, okay, next week, who do I call? Which 2? So she may choose these remaining 2. Unfortunately, this turns out to be a bad choice. Not only these 2 mothers did not start listening. In this case, the first 2 mothers who are listening have also turned red. They are not listening anymore. The point here is that we have challenges. A service call may not change a beneficiary state from red to green, and a beneficiary may change state on their own from green to red or red to green. And despite these changes happening, we have to prioritize 4,000 beneficiaries per week. So how do we do that? We cast the problem as a restless bandit, where we are trying to choose K out of N arms per week. For those who may not be familiar, in a restless bandit, each arm is modeled as an MDP. So mother might be in a bad state. She has not listened to any messages last week, or good state. She has listened to a message this week. And there's transition probabilities of going from bad state to good state. There are actions that are possible to do. We can give her a service call or not. If we don't give this mother a service call, there's a higher probability the mother may remain in a bad state, that she keeps not listening to messages. If we give her a service call, the transition probability from bad state to good state is higher. She is able to transition to a good state listening to messages. So in reality, we have we have these 200,000 arms, so 200,000 mothers. Each of them is an MDP. And we are trying to select 4,000 out of this. This is a massive scale problem and difficult to solve. So these kinds of problems get solved by computing a Whittle index of each arm. The Whittle index is basically computing the benefit of intervention on each arm, each mother. And then we choose the top K arms. We choose the top K mothers who would benefit the most from the intervention. There's a particular algorithm from Chen et al. March 2016 that we use to do this computation. And for those who want to know, basically a Whittle index at a particular state is the minimum amount of subsidy that can be given so as to make the utility of not calling from that state equal to the utility of giving a service call in that state. And so that's essentially the definition, but it's basically computing the benefit of intervention. So what's the research challenge here? Normally, the transition probability in this model is supposed to be known, but we are faced with the problem that these transition probabilities are unknown. We do have past beneficiary data, though, in terms of mothers, the features of each beneficiary, their age, income level, education level, etc. An engagement sequence, meaning for past several weeks, were they listening, not listening, how did they transition based on a service call or no service call, etc. So based on this past data, we can use a training step whereby we cluster these mothers into different clusters, and then learn a mapping from features to clusters. So mother of a certain education or income level will have a certain transition probability. Then when a new mother comes in at testing time and a new beneficiary joins, based on their features, age, education, etc., we can predict their transition probabilities, from where we can compute the Whittle indices and then choose the top K mothers to intervene on per week. So this kind of clustering helps us compensate for the lack of data and also speeds up our Whittle index computation. So we've recently completed a study with 23,000 beneficiaries. This is a field study, this first large-scale application of restless bandage for public health. So again, we had 3 groups. One was a restless bandage group. So these were mothers, 7,667, where we chose who to give service calls to based on the restless bandage algorithm. One was a round-robin group. So we sequentially chose mothers one group after another, and a current standard of care group where there was no service call given. We pulled 225 arms per week. That is, we called 225 mothers per week for 7 weeks. And then we want to look at how many more health messages were listened to over the current standard of care group in each of these different groups. And here's what we find. On the x-axis here are weeks, on the y-axis is cumulative number of messages more that are listened to compared to the current standard of care group. And we find that with the restless bandit group, there's more than 600 more messages that are listened to. And with the round-robin group, there's very little difference. In fact, in terms of statistical significance, we find that the difference between the restless bandit group, RMAP group, and the current standard of care group, this is significant. Round robin versus current standard of care is not significant. So this is telling us that the optimization of service calls using this restless bandit approach is important. If we just give service calls based on something like a round robin approach, one group after another, that fails to have any statistically significant improvement over not making any calls at all. We are now launching a new 100,000 beneficiary study, and our ultimate goal is to transition this software to Armand so that they can use it. Here's what the founder of Armand, Dr. Aparna Hegde, had to say about this work. She said, we are able to reach out to more and more women each week and get them back into the fold and save lives because of AI. And there's this YouTube video from Google on AI for social good in partnership with Armand. If you're interested, have a look at it. It also shows mothers who got back into the program because of these AI targeted service calls. And they're following, and what they point out is like, because now they're back in the program, this mother is saying, I'll follow all the advice and take good care of my baby. It's a well-made video. If you have time, I recommend that you look at it. So, whereas Armand and having mothers listen to these phone calls is one application of restless bandage, there are others. Tuberculosis, for example, is one problem where there's 500,000 deaths per year in India, 3 million get infected every year in India. And a patient has to follow 6 months of pills. So they have to take 6 months of pills in order to recover from TB. This is an extremely difficult task. But again, if a person doesn't complete this course of taking these pills, it's not only bad for them, but that leads to drug-resistant bacteria. So again, health workers are tasked to try to make sure that patients complete their course of 6 months of pills. So imagine now, again, a health worker at a call center trying to figure out who to call, and she has a number of patients in her care. This problem seems similar to what we have seen before, except whether a patient took their medicine or not is not known. So this health worker can give a call to, let's say, 3 of these patients here, and at that point know that 2 of them took their medicine and 1 did not. And then she has to decide next week who to call based on what was next day who to call based on what she has known, and go on in this fashion. So the problem is similar to what we have seen before, except that the state of the patient, whether they took their medicine or not, is not known. And so we solve this problem again by using this restless bandage, but there's a small variation, and it's called collapsing bandage. Basically now, when an arm is not played, that means a patient is not called. We have no observation about that. We don't know if they took their medicine or not. So we essentially update our belief about this patient. When the patient is called, though, they may say that I took my medicine last night. So that means uncertainty collapses. We see this green. That means we know the patient took their medicine. Or that the patient didn't take their medicine, shown in red. So certainly the uncertainty we had about whether the patient took their medicine or not collapses by giving a call. And we use this collapsing approach to build a fast algorithm, and we can prove some optimality properties based on this collapsing approach. We can show that our algorithm, which is shown in blue, is much faster than the baseline without giving up much in solution quality. There are many other very interesting challenges in machine learning. I'm going to skip over some of these slides in the interest of time and go to the third topic that I wanted to cover, which is COVID modeling. So this is, in the past year, we've done some work using agent-based modeling for COVID, and this was work done jointly with professors from the Harvard School of Public Health, HSPH. I'm going to highlight one of the papers here from Science Advances because this gets referenced very often in the media. So for example, this is one paper that was done jointly with Professor Michael Mina, who's a leader in this space. And the question here that we were asked is that Michael was struggling with is, we have, places like Harvard where when COVID struck, what kind of testing strategy should we use? Should we test all the students using something like the PCR test, which is a gold standard, which detects very low viral concentration, but just happens to be more expensive, and it takes 1 or 2 days to get the results back, versus an antigen strip, which can only detect high viral concentrations, but is cheap, and we get results back in 15 minutes. So now if you're Harvard and you're trying to figure out, we want to test our students every day or every few days, should we be using a PCR test or should we be using an antigen strip test? So Michael posed this as a modeling problem for us, and we were glad we could help with that modeling. So indeed, if we look at testing all of the students, so in this model, on the y-axis are the total number of infections. Orange is the result of this antigen strip, less sensitive. So basically in this approach, we are going to test all of the students, and anybody found positive is going to be isolated. And in this case, in this first situation, we are assuming that test results come back instantaneously, and we're testing students every 3 days. Indeed, in this case, it turns out that blue is lower than red. The more sensitive test is better. The PCR test is better in reducing the total number of infections. However, as we said, the test results are actually not available instantaneously. The PCR test may take a day's delay to get us results back. So 1 day's delay in isolating individuals. That 1 day delay means that we lose all our advantage of having this more sensitive test. There's a much higher number of infections. Because of cost, furthermore, if we can only run this test, the more sensitive test, every 5 days instead of the every 3 days that's shown in orange, again, the advantage of the more sensitive test is lost. The point here is that rapid turnaround time and frequency is more critical than sensitivity for COVID-19 surveillance. That is, this antigen strip turns out to be a better test. This work received widespread attention in New York Times and Washington Post and Time and many others. We were thrilled when Dr. Anthony Fauci talked about this paper in one of TV programs. And of course, Dr. Michael Mina, who's our collaborator to whom all the credit belongs, has been advising at the level of President Biden's COVID task force and has been a leader. So we're just very glad that we could assist him in some of this modeling work. I see that we are about 35 minutes into this talk. I'm going to speak for about 10 more minutes and then open it up for questions. And here I'm going to switch over and talk about poaching prevention as the last project. And here I'm going to talk about game theory and behavior modeling. So in conservation areas around the world, there's wonderful wildlife, like in the Queen Elizabeth National Park in Uganda, but there's also threats to the wildlife, traps or snares that get placed by the thousands to maim and kill wildlife. And rangers have searched these parks trying to look for these kinds of traps or snares. So you can imagine this is an extremely difficult task for a small number of rangers trying to patrol thousands of square kilometers of national parks. So can we assist them? So we can divide up this park into 1 kilometer by 1 kilometer grid square and then give rangers directions of where to patrol based on this 1 kilometer by 1 kilometer grid square. So we do that by modeling this problem as a game, whereby on the one side are rangers, on the other side are poachers. So I'm showing you here a game over just two of these grid squares, but of course there are thousands and thousands of grid squares in any national park. So you could imagine that given these two areas to patrol in this simple game, if the ranger always tries to patrol one area, area 1, then a poacher conducting surveillance, the poacher will know where the ranger is, and the poacher will go to area 2 and lay a trap there for animals. So any deterministic strategy where the ranger always goes to one area or patrols the areas in a very known order can be defeated. If, however, the rangers use a randomized strategy, a mixed strategy, so that 60% of the time they're in area 1, 40% of the time they're in area 2, chosen at random, a poacher may not know what the ranger is going to do tomorrow, and this can deter poaching. Now, in the past, as I've shown you, we've done these kinds of Sackleberg security games, as they are called, and deployed them in the context of the TSA or the US Coast Guard and others, where we are faced with very strategic adversaries. Here, we are looking at boundedly rational poachers. They're not conducting surveillance over the entire park. They're not thinking very strategically. And instead here, there's a lot of past poaching data available. We're going to learn their behavior from the past poaching data. In terms of the data to deployment pipeline, what we're saying is we have data that's collected about poaching. We're going to use that to make predictions about where poachers are going to lay traps. And then having predicted poaching locations, we are then going to prescribe how to patrol based on our game theoretic model and then test it out in the field. So we are now in the prediction stage, trying to predict poacher behavior. And we are going to do so by looking at past data. We have 14 years of data from Uganda that we had at that time. And so there we have, for each grid square, ranger patrol frequency, we know the animal density, distance to rivers, roads and villages, area habitat and other features. And based on that, we can build a model. I'm going to skip over some of the details of that model, how we build a predictor for poaching, where poachers are going to set traps. So there's some ensemble model that's in our paper. So the first test of this was in the Queen Elizabeth National Park that was done in the fall of 2016. We selected 2 9 square kilometer areas that were infrequently patrolled. So if we told the rangers to just go back to where they were patrolling before, that's no use. We want to tell them that there are new areas that they were not patrolling where we are going to recommend they patrol because they're going to find new poaching incidents. And those are shown in green, whereas the red shows where the rangers had found snares in the past. And so we asked the rangers to go patrol these areas for a month. The rangers went out to patrol every day. They would send back reports as to what happened there. Initially, there was nothing. And then they reported they found a poached elephant. The next day, they found a whole elephant snare roll and removed it. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, a whole elephant snare roll was removed and thus potentially saving lives of elephants. Following that, 10 antelope snares were removed. So this pilot test was successful in identifying new areas to go patrol and remove snares. So now it was time to do a larger scale test, and this was done in 3 national parks: Queen Elizabeth, Murchison Falls in Uganda, Sripak Wildlife Sanctuary in Cambodia. There were 24 areas selected in each park that were infrequently patrolled, and we predicted that some of these were high-risk areas, more snares would be found, and some of them were low-risk areas, less snares would be found. It was important because if we just say that any infrequently patrolled area is where snares would be found, this would not be useful. What we are showing you here is that we can discriminate between high-risk and low-risk areas among those that are infrequently patrolled. And so having made these predictions, rangers went out looking for traps for 6 months in these areas, and where we predicted high risk, indeed more snares were found. Where we predicted low risk, less number of snares were found. And this was consistently seen in all 3 parks. In fact, these are pictures from Shripok Wildlife Sanctuary where rangers have found snares. Whereas in 2018, they were finding about 100 snares per month. The number of snare captures jumped 5-fold once our pause system for making predictions started getting used. Even in 2021, 1,000 snares were found in March with the help of pause. So this success in being able to make predictions and remove snares has been recognized by SMART, which is a collaboration of many wildlife conservation agencies. And so they have integrated our pause system with SMART, which means that this pause prediction system for predicting where snares are found is now available in hundreds of national parks around the globe. It's been tested in the field, and people are downloading this software. It's a very exciting time in terms of what we can do to assist in the hard work that the rangers do in the field. So I'm going to quickly talk to you about some of our next steps and then stop and take questions. So having done these predictions, the next step is do prescription, that is doing recommendations on where to patrol using game theory. But one of the questions here is, do poachers actually get deterred by patrols? Because if the poachers are not paying attention to any of the ranger patrols, it doesn't matter how we patrol, they just don't care. Is that the case? What we find is we built a model, a logistic regression model here, trying to see how we can fit the data. So we would expect that current patrols would have a positive correlation because the more you patrol, the more snares you found. But past patrols should deter poaching. And indeed, what we find is that there's a positive coefficient on the current effort. So more patrols lead to more snare captures. This year, if you patrolled more, you would find more snares. But if there were more patrols done in an area last year, in fact, there's a negative coefficient, meaning in those areas where there were more patrols last year, there'll be less poaching this year. So this shows that the adversaries poachers are actually getting deterred by patrols. This is important as we build our game theoretic model. And again, we build this sort of a zero-sum game against nature to build robust patrols because we have a model of how the adversary behaves, but the coefficients are not exactly known. And so we can assume there's uncertainty over that and solve that as a zero-sum game to generate patrols. I'm going to just mention some work that we've been doing with another NGO called Air Shepherd that we did. They fly drones in South Africa looking at infrared imagery on the ground. And from that, we're trying to detect if there are poachers that are seen in this infrared video. And so for that, we built a system called Spot that automatically detects poachers and wildlife. I'm going to skip over some of the newer challenges that we are looking at in terms of data scarce parks and so forth, and come to some of the lessons we have learned and then stop and take questions. So as I said, achieving social impact and AI innovation goes hand in hand. Our ultimate goal is to really empower these nonprofits to use AI tools and avoid being gatekeepers to AI technology for social impact. We are interested in the entire data to deployment pipeline. We're not just about improving algorithms. It's important to integrate AI innovations in the NGO's normal workflow. It's important to step out of the lab and into the field. If we just are sitting in our lab and giving instructions to a wildlife conservation agency to patrol in the field, it doesn't work. We've seen this firsthand where we were in our lab trying to give instructions to patrollers in Malaysia to say, hey, you should go from point A to point B, and not understanding that the terrain was very hilly. And didn't lead to good patrol. So going there and actually seeing the terrain was very important to come up with good patrolling recommendations. It's important to embrace interdisciplinary research in terms of social work or conservation. And finally, lack of data in this area of AI for social impact is the norm. It's a feature and should be part of the project strategy. We can't just complain and say that, oh, there's not much data here, I'm going to skip over and not do this project. So thank you for listening to me. And if you wanted to follow more on some of the work that we've been doing, that's my Twitter handle, where I tweet regularly about our work on AI for social good. And so thank you again, and I'll stop here and take any questions you may have.
Oh, thank you so much, Milind. You presented many impressive examples of pushing the state of the art in AI, working with community and research partners on a wide variety of activities on AI for good. We've got quite a few questions in the Q&A session, but I might jump in with one of my own first.
Sure.
So a step before the work that you present is actually forming the relationship with the community group. Can you say anything about how an AI researcher who wanted to follow in your extraordinarily large shoes might set about forming such relationships?
I don't know if my shoes are that large, but I will provide several examples of how this can be done. At Google Research India, we have been running a program for matchmaking between faculty members who want to engage with nonprofits and nonprofits. So, for example, we did this program in 2020 and then 2021. We issue a call regularly. It will come out again in the spring of 2022, where a faculty member can apply to this program. And then there are nonprofits who also apply to the program. And then we have each professor meet with 3 nonprofits, and each nonprofit meet with 3 professors. And then they write joint proposals, and then we fund them to do this work in AI for social good. And in 2021, we funded 30 such projects with nonprofits, in this case, in Asia and Africa, and faculty members drawn from around the world, including from Australia. So similarly, we'll run something in 20. So that's one.
So just jumping in there, so if one of our faculty would like to join in that program, what would be the pathway to getting involved?
So we will, there'll be a call from Google Research on AI for social good. And we publicize it. I mean, we'll try to publicize it even more. And then basically just, it's a very simple application saying who you are and, what's your area of interest. And then the trick is really meeting with the nonprofits and writing a proposal. So that's one way in which, so that's one. Other ways I have found useful is in the Boston area, for example, we invited at our center some nonprofits from around Boston area to come in and talk to our faculty members. And so again, there's sort of a mini matchmaking where the nonprofits came in and they made some presentations about the kind of data they have and kind of needs that they have. And then based on interests of faculty members, we ran simple matchmaking and that led to some projects here. And so these are sort of examples that I can imagine, but I understand, I mean, this is not easy. Relationship building takes time. And another thing I've done in the past is also to work with faculty members who already have deep community connections, like in social work or conservation, and collaborate with them because they have those relationships, and then that allows me to work. So there are many avenues that are possible to follow up on building up these connections to nonprofits.
Thank you very much. We might move some of the questions from the Q&A. So the first one related to the very early slides where you were talking about influencing a network of 6,000 people through influencing the peer leaders. And the question is, how did you identify those peer leaders?
So the key in the algorithm that we use is really network structure. So the algorithm is trying to identify a few nodes that are strategically placed in the network in order to maximize this information spread. So you can imagine that the previous strategy was to choose the most popular youth, the youth who have the maximum numbers of connections. But they tend to all be in the center of the network. And they're all connected to each other. So they all seem very popular. They're all connected to each other. And this leaves uncovered many of the different parts of the network, many of the sub-networks are left without any coverage. So the algorithm is trying to find people who are strategically placed so that they can spread this information in a maximum. So it's only looking at network structure. It's not looking at any other feature, their gender, race, whatever, nothing. It's only looking at the network structure to identify who's key, where are the key nodes that we can select for influencing.
Thank you. Bernd Mayer has a question. He starts out by thanking you for a very impressive talk. And I would second that. So he is tackling the other side of my question. So I was inviting you to reflect on how you get AI people to connect with the social partners, but he's wondering whether you can comment on how you convince potential community partners of the potential value of AI models, which can be quite foreign things and very difficult for them to get their heads around.
No, this is a very important question, and in our experience, it's not always very easy. The first meeting I had, we started all this work on AI for social impact out at the airport in Los Angeles, trying to help them with their counterterrorism strategies. And I remember the very first meeting we had, there were obviously some leaders who were very much with us, but there were people in the audience, the police officers, were sitting there and saying, we have decades of experience. What can AI teach us that we don't already know? And I agree. I mean, this is not an easy task. Relationship building, trust building takes time. And we often will, show over a period of time by building up these AI models in collaboration with the particular partner and showing them that it does provide some benefits over the way they were doing things in assisting them. And I have this very wonderful example where we were working with the Los Angeles Sheriff's Department at one point. And initial meetings were a little bit, the Sheriff's Department people weren't too happy with my team. But my students went on patrols with the Sheriff's Department on the trains, and over time built up a relationship to the point that when finally there was a demonstration of an AI program against the human scheduler. And scheduling is a really tedious task of, where to schedule, but it's really complicated. And instead you have an AI program that is assisting these people to come up with schedules. So we have a purely human schedule and an AI schedule helping people. And the AI program did much better, according to external observers, than the human program. Instead of getting upset at the AI program, we found that the sheriff's people were actually hugging my students and talking to them and saying, look, you have shown us a better way of doing things. And so I guess my point is that it's not an easy task. It takes time, relationship building up trust. And we found that, but eventually after demonstrating actual improvement in the day-to-day work, we found that people do come around. Not always. We've also had situations where in some cases, there's just no success. I've been to a wildlife conservation agency in a country where, we were the minister was talking about, we should use AI and advanced technologies. And we talked to the rangers on the ground and they were saying, we just need better shoes now. We don't need anything more. And so in that case, this was just not a good solution. So yeah, it's a very important task, and this partnership building doesn't always succeed.
So reading between the lines in your answer about the Sheriff's Department, then, is it also fairly critical the selection of what tasks you select to work on first? So you gave an example there where it was a task where they don't really like doing it. So if you can automate it, then there's not going to be resistance to replacing an existing approach with theirs.
That's an excellent point that, we want the AI to be only focused on things that it knows better. So for example, looking at past patterns of data, predicting which square kilometer to look at for finding poacher snares and traps. But we are not going to tell the rangers, okay, which tree might the snare be hidden under, or which bush. Those are things that the rangers know much, much, much better than what we are able to do. So there has to be a balance between what the AI technology knows best and what, the expertise that people have, and that partnership is important.
Thank you. So Morgan McLeod Fink has what might be viewed as a follow-up question to Bern's earlier question. So it's one thing to convince the community partner that AI might help them. What do you need to do to then empower them to be able to actually utilize a technical solution when they're likely to not actually have much technical expertise?
That's again an excellent question, because you may run a pilot, you may run a, maybe even a small scale program, but then eventually you want to transfer the software over to them and they need to be able to run it. And we've certainly found that this means that we may have to scale down we may write a paper with a very complicated model that takes very high computing resources and so forth, but this is unaffordable to a nonprofit who may be running on a shoestring budget. And so we may have to make the model much simpler, make the interface much more intuitive. In some cases, what we found is we found both. In some cases, there's a normal workflow. If the nonprofit is already, or whatever government agency is already using some kind of a simple software, that whatever our AI solution, we make it appear as though it's in their normal workflow. Just like what they were doing, the interfaces look exactly the same, except the backend has changed and is using something more sophisticated. So there's no interruption to the normal workflow. So that we found important. In some cases, we've kind of gone overboard and, okay, now we're going to give you this very complicated interface and, red, blue, green, you can train people. But we found that the sorts of things tend, people may not actually use it. And so get rid of a lot of complexities and just give something very simple for people. So I think low resources, in terms of low computing resources, making sure that things are integrated in the normal workflow. Those are some of the things that we've done in order to make sure that the software gets used. But this is an important problem in terms of how do you continue to support the software and so forth after you've delivered it to a non-profit, so that they can continue to support it and we can continue to maintain it. And that's just not very easy. And we found you need someone else to then pitch in terms of funding, in terms of technical expertise. So it's an excellent question. I don't have a very general solution. I end up just sort of taking resources from where I can find it in order to continue to support these kinds of efforts.
So a question from Bronwyn Evan. Oh no, sorry, we've already answered that one. From Min Lee. So assuming many poor people get pregnant, have TB or other serious diseases, and they don't have phones or internet connections, do you have any insights about how they might be connected contacted by other kinds of mechanisms, or is that beyond your?
So that's a good question. I guess in India, for example, cell phones and data have become so cheap that it almost seems like every person has a phone. It's just become very cheap to have phones, and data is really cheap. And so that's what a lot of these nonprofits are. That's what they're leveraging in building up these massive scale programs that reach people, whether it's for TB, for maternal and child care. And so yeah, that's what we are leveraging. If we don't have that, we then build on top of those kinds of programs to assist them and optimizing their service. But if that doesn't exist, then I'm not sure exactly how one would reach some of these folks. So that's beyond my expertise in some way.
Thank you. So we have an anonymous question about, so they're interested in the pause work, and they were wondering what kind of factors you need to measure there, whether just measuring the number of snares is enough, or whether there are further factors.
So we interface with this software called SMART, which is used around the world by organizations like World Wildlife Fund, Wildlife Conservation Society, and others, and that automatically collects the GPS location of the rangers. So what this means is we have data not only on where poaching incidents have happened or snares have been found, but also patrolling frequency in different parts of the park. And that's important because that allows us to build a connection between past poaching, a past amount of patrolling and poaching, because as we've shown, past patrols deter poaching. So we need to know how much past patrolling happened in a particular grid square. We also have a connection between amount of patrols that were done in a particular grid square and the number of snares that are found. So depending on the different kinds of parks and so forth, that relationship also varies. In other words, we need information on amount of patrolling that was done in addition to poaching incidents. And then there's other kinds of information that you can just get from GIS, and basically for each grid square, for each location, how far away is it from the boundaries of the park? How far away is it from rivers, from roads, from close by villages and so forth? But that is something that you can get from just satellite imagery or from GIS and so on and so forth. And so we use all of that in order to be able to make predictions. If you don't get any of these features, then it does become more difficult to make predictions on poaching incidents.
Thank you. We have a question from Devesh Singh, who says they're very new to the AI field, but they generally have the impression that state-of-the-art techniques, such as deep learning, aren't that accessible for social good applications, and they were wondering what your thoughts are on that.
I mean, it's a good point. I think so we don't necessarily rely on deep learning for many of some of these applications. We are not really relying on deep learning per se. In fact, in the wildlife conservation work, we have a paper where we show like a very complex model based on Gaussian processes and so on and so forth is the best in terms of actually delivering results. But when we try to deploy it in practice, it turns out that the computational cost is unaffordable. Purely the amount of computational hardware for the agencies that are actually going to use that model. And so ultimately, it's relying on something much simpler, which is just simple decision trees and ensembles of decision trees and so forth. So what I'm saying is that we can achieve things with fairly simple AI models as well, if we are trying to achieve that kind of social impact. It depends on the problem, of course. In some cases, though, it is important to learn the right kinds of models and the right kinds of tools, because it depends. I mean, as I've shown you, in some cases, we relied on these bandit algorithms. In some cases, it's social networks. In another case, it's a game theoretic model. So it really depends on the kind of application that we have in mind in order to apply.
So in the examples you gave, you were showing quite extraordinary technical prowess and pushing the boundaries of the state of the art in each of the problems you tackled. How often do you think it's really necessary to do that in order to be able to provide good solutions for these problems, and how often is it really more a question of working within the current state of the art?
So I think there's 2 points here. As research AI for social impact researchers, we are looking for problems where we actually are going to advance the state of the art. So in some sense, if there's a problem whereby a simpler solution can apply, then that's something that we may not take on. We may leave that for people who, for example, who may be able to take that on, because that's not necessarily advancing the state of the art of AI in some way. I mean, it could be, it could be in different ways, but anyhow, so that's kind of my job, is to find out these problems where the problem is just difficult enough so that we can advance the state of the art and actually arrive at some kind of an impact. But those are not the only kinds of problems that are out there. There are problems whereby we don't have to necessarily advance the state of the art. A lot depends there on coming up with the right model and then using the state of the art. And, I've had these kinds of courses that I've taught where I'll invite social work students and AI students in the same class and form teams. And there we often find that the social work students would have problems at hand that they're trying to struggle with their data. And the AI student can apply a standard state-of-the-art technique to deliver impact. And so there's I guess what I emphasized today was more a set of problems where we had to both advance the state of the art in order to show impact, but that's not always necessary. And these interdisciplinary partnerships that I mentioned would be important to kind of focus on the right kinds of problems, depending on what one's interest is, whether to do more AI research or do much more on social impact side.
So to flip that question around the other way, some of our AI researchers, their primary interest in doing applied work is to have drivers for doing fundamental work which will advance the state of the art and which is hence publishable. What would you estimate the hit rate would be if you're looking for those types of problems in these types of fields?
I guess, if you've been working in this area, right, for a while, then you kind of get a sense of, okay, this is a problem that seems somewhat straightforward and may not, there's not much of an opportunity to advance the state of the art in AI, where there are others we can see. So I guess in terms of hit rate, it would depend on, the practice that we've had in terms of identifying which problems need that advance and which problems don't. So it's kind of hard to give a general answer as to what the hit rate would be. But my general sense is that if you go deeper into, you start talking to any of these agencies and get deep into their problems, most often there is a problem that they're struggling with where, this is a problem where we will have to advance our AI techniques just don't quite work. We'll have to make some advances. So there may be some problems where they say, okay, this is estimate, gestational age of, based on a woman's sort of reporting or something like that of the child in one of the applications I mentioned. There's data, there's, you can use standard state-of-the-art techniques to do that. But then you talk more with them and they say, okay, there's a much more, a deeper problem that they're struggling with where you'll have to advance the state-of-the-art of AI. So I guess what I found often is that I have my friends in World Wildlife Fund, for example, and I call them like a storehouse of problems. So anytime my PhD students have problems, anytime my students in my class have like what problems, we bring them in. They say, okay, here's tons of problems that we're facing. Some of them are PhD level problems, some of them are undergraduate level problems, and they just have all these things for us to work on.
Fantastic. And then one final question. So Jessica Walsh, and thank you waiting so long, Jessica, for us to get to this one. So I think you gave one example where you looked at a problem and it ended up that you weren't able to develop a AI solution to it. And Jessica, I was just wondering if you have any further examples where you're where the desire to apply AI has just not been able to turn into effective solutions.
Certainly, there are others. Sometimes there are partner agencies who are not interested. I mean, sometimes, like I said, there's a situation where they just wanted better shoes, but there are others where even the higher ups are just not that interested in using AI for whatever reason. And no amount of discussion and partnership building and all of that is of any use because they're just not that keen on using AI. That has certainly happened to us in some cases. So, I guess the other thing is early on, I mean, when I didn't have this, I mean, right now I'm fortunate to have this position with Google in India where I can be on the ground and have partnerships. Early on, when I was trying just on my own, it was difficult because I just didn't have, building up partnership means that you have to be on the ground, you have to have meetings and talk to people and so on and so forth. And so early on, I had difficulties building up those relationships. So we would have very interesting, exciting first conversations to protect wildlife or what have you. And then, things would fizzle out because there's no follow-up and so on. So, yeah, I mean, there's plenty of examples where things haven't worked out in terms of building up something in terms of an AI solution. So, yeah, I guess for Jessica, she's involved in some of these efforts. It takes patience, and not everything succeeds as would be expected.
Well, thank you very much, Milind, for leading us today for a wonderful presentation and a tremendous discussion. It's been an absolute pleasure. The questions keep coming in, but I regret that we have run out of time. We'll send any remaining questions to you. So if anyone has a final pressing question, then type it into the Q&A very quickly. So as a reminder to our audience, we'll continue the Monash Prato Dialogue lecture series in 2022. Up next, we have Professor Rosaria Taddeo from the University of Oxford on the 10th of February, so mark that in your calendars. We invite you all to stay engaged with the Monash Data Futures Institute and to attend our upcoming events. We encourage you to follow us on social media, both LinkedIn and Twitter, and to join our mailing list by signing up for our affiliation program through our website. And thank you all for joining us. You've been a wonderful audience. I'm really looking forward to seeing you again in our future Monash Prato Dialogue Distinguished Lecture Series and joining us for these valuable and provocative discussions. And thank you so much again, Milind, for leading us in such a fantastic, informative and inspiring event today.
Thank you again for inviting me. Thank you. Bye.
Thank you. Bye.